Welcome back. In this video, we're going to begin doing chapter 15 of the Chem 110 ebook, looking at chemical reactions and focusing on reaction types. After reading the text and watching this video, you should be able to classify reactions as being either combustion, combination, decomposition, exchange, or double displacement. You should be able to balance these types of chemical reactions, as well as predict the products of these reactions, and as well identify the driving force for aqueous exchange reactions. So let's first talk about some underlying principles here. When we do a chemical reaction, mass is being conserved. What this means then is that the amount of the mass of the reactants is going to be equal to the mass of the products. During chemical reactions, this occurs because what we're changing is how the bonds are formed and where the electrons are, but we're not converting material into energy, which is the case for nuclear chemical reactions. So no matter is created or lost during a chemical reaction. As I said earlier, the mass of our reactants must be equal to the mass of the products. Therefore, the number of each atom of each element must be equal both in terms of the products and the reactants. So for example, this is a reaction that is the combustion of ethane. And to interpret this, we need to understand that the coefficient in front determines the number of each molecule, where the subscript will help to identify the molecule itself. So what we see here is that we have 2 ethane molecules reacting with 7 oxygen molecules to produce 4 carbon dioxide and 6 water. When you count up the number of each element, you can see that we have 4 carbons as a reactant, 4 carbons as our product. Carbon is indicated here in gray. Hydrogen is white, and there are 12 total hydrogens in the reactants. There are 12 in the products. And oxygen is red. There are 14 oxygen atoms total, both on the reactant and the product side. So this is called the law of conservation of mass, and it's important to understanding how to balance chemical equations. Let's now talk about different patterns of reactivity that account for the different types of chemical reactions that we'll be seeing. We've already looked at combustion reactions. Within a combustion reaction, we are generally taking a hydrocarbon, and what we're doing with it is we're combining it with oxygen. So we will always have oxygen in a combustion reaction. The products are going to involve carbon dioxide and water, and possibly some other things, depending on if we had nitrogen or sulfur in our hydrocarbon as well. But the most important aspects are that you understand that we are reacting with oxygen and that our products are carbon dioxide and water. Our second type of reaction pattern is what we call a combination reaction. As the name implies, a combination reaction is when we combine 2 substances to form 1 substance. So in this case, we've taken and we've added magnesium and oxygen to form magnesium oxide. We could also take and combine 2 different molecules. So in this case, we have calcium oxide and carbon dioxide, which combine to form calcium carbonate. The number in front of our products does not matter. Rather, what is important is that we're taking multiple components and combining them into 1 component. The opposite of this process is a decomposition reaction. In a decomposition reaction, we're taking 1 particular compound and we're breaking it down into multiple other compounds. So again, likewise here, the number of a given reactant does not matter, but rather the fact that we are only taking 1 reactant and we're forming multiple products out of it, each of which is its own molecule. For aqueous solutions, or in other words, solutions where the solvent is water, There are a couple other types of chemical reactions that we see. We have single displacement reactions. For example, you could take zinc metal, it reacts with an aqueous solution of copper sulfate, and that produces zinc sulfate and copper solid. We see this is also classified as a redox reaction, and we'll learn more about redox reactions in a future video. We also have double displacement reactions. These are also known as metathesis or exchange reactions. Double displacement reactions typically have a driving force such as formation of a precipitate, as is here with lead nitrate reacting with potassium iodide to form lead iodide precipitate. We could also form a weak or a non-electrolyte, as is shown here in the formation of water from sodium hydroxide and hydrochloric acid. Water is a non-electrolyte. And then finally, the formation of a gas, as is illustrated here with the reaction of hydrochloric acid with sodium sulfide to produce hydrogen sulfide gas. Notice when you compare single displacement to double displacement reactions, that for single displacement reactions, you have a solo atom or molecule, and then you have a combination. And we're essentially swapping places. For a double displacement reaction, we have a cation and an anion in both of our reactants, and those are swapping places. So we could say, imagine what's happening when our anions swap places and the products that they might form. Let's do a practice problem here. Let's identify the coefficient in front of water in the balanced reaction for the combustion of ethanol. How do we do this? Well, when we're talking about a combustion reaction, we know that we're taking our hydrocarbon and we're reacting it with oxygen to produce carbon dioxide and water. So let's start by writing out a general chemical equation. So we have our ethanol reacting with oxygen to produce carbon dioxide and water. Now, what we want to do is we want to balance each of the elements. When you're trying to determine which element to balance, the most important thing is that you pick an element starting in the reactant side that only shows up once on the reactant side. So you'll notice here that oxygen shows up as a reactant in two different molecules. Therefore, trying to balance the chemical equation using oxygen first would be very, very difficult. It's made even harder by the fact that oxygen shows up in two different products. So we need to identify one element that shows up only in one reactant and one product. Notice that carbon is only in ethanol and it's only in carbon dioxide. Hydrogen is only in ethanol and only in water. So either carbon or hydrogen would be a good choice. For this example, I'll show you how to balance with carbon first. So we see that on the right-hand side, we only had one carbon. On the left, however, we have two carbons. So in order to balance the chemical equation with respect to carbon, we need to place the coefficient 2 in front of carbon dioxide. Now, in the reactants and the products, there's two carbons. Now let's take a look at hydrogen. Hydrogen has 6 hydrogens in our reactants and 2 hydrogens in our products. So in order to balance it, we need to put a coefficient of 3 in front of the water molecule. The last step would be then to balance oxygen. Now notice that by adding in the coefficients in front of carbon dioxide and water, we've changed the number of oxygen atoms on the product side. This is why it would be difficult to balance oxygen earlier. So now what we see is that we have 4 oxygens from the carbon dioxide, 3 oxygens from the water, and on the reactant side, we have 2 oxygen from the oxygen molecule and then 1 oxygen from the ethanol. So in order to balance, we need to put a coefficient of 3 in front of the oxygen molecule. Then You always want to check your answer. Add up the numbers of each atom on both sides of the equation, and as long as they match, then you know that you've done it right. That's it for this video. Thanks for watching. Have a great day.